Hi, good morning. Nice day wishes. How are you? Hope you are doing well. We are dealing with complex numbers today. So, as the name indicate, complex numbers, it's not so much complicated. It's so easy. So, welcome to the topic. Welcome to the kingdom of complex number. So, what is a complex number? We are already having familiarized with the quadratic equation. Uh, This is a quadratic equation. So what is the solution of this equation? Here it is x square plus 1 equal to 0. That is x square equal to minus 1. That means x square equal to root of minus 1. So this is not defined, right? So in this case, we can write it as I equal to root minus 1. Okay, so uh, a complex number is a number which is having two parts, real part as well as imaginary part. We can write or we can denote complex number as z equal to a plus ib. Okay, so here the first part or first part A. First part or maybe A is known as real part of complex number. That is real Z equal to A. And here the imaginary part Im of Z equal to B, where A and B both are real numbers. Okay, so are real numbers. Okay. So a complex number is a number which can be expressed in the form of a plus ib, where a real part of the complex number, real z equal to a, and imaginary part of the complex number, im z equal to b, where a and b are real numbers, where I equal to or iota equal to root of minus 1. This is a complex number. So in fact, a complex number is a superset of real numbers. We can, express a complex number and in the form of real plus imaginary number. Okay, so that's it. And if here a is 0, if a is 0, that means there is this complex number don't having the real part. So such complex number is known as purely imaginary. If a is 0, if a is 0, sorry, if a is 0, then this complex number is purely imaginary, right? If b is 0, if b is 0, this type of complex number, this part will not exist. That is, only real part will exist. This kind of complex number is known as purely real. Okay. And also, we are dealing with another concepts like if two complex numbers, that is z1 equal to a1 plus I b1, z2 equal to a2 plus I b2. If two complex numbers z1 and z2 are equal, then their corresponding real part should be equal and their corresponding imaginary part should want to be equal. That is, if z1 equal to z2 implies a1 equal to a2 and b1 equal to b2. Okay, fine. So you got the idea, the basic idea of complex number and its properties like when two complex number are equal and what is purely imaginary and purely real complex number. Okay, and what is iota. Okay, fine. So that's it. And we are moving to the next topic, that is the properties of algebraic operations in complex number. As like numbers, we are dealing with some algebraic operations like addition, multiplication, subtraction. Basic algebraic operation are also conducting through complex numbers. So if we conduct those algebraic operations, we can find that uh, in algebraic operations like addition, multiplication of complex number, it is always commutative. If two complex numbers are adding, z1 plus z2, that is always equal to z2 plus z1. Okay, so that kind of property is known as commutative property, that is applicable for other operations as well. Okay, and always complex number operations are closure. If two complex numbers are adding, or if two complex numbers are multiplying or subtracting, then again we will get another complex number. Such kind of property is known as closure property. So complex number operations always may be commutative, or maybe as I mentioned, closure. And next property is associative. Okay, so for this, like z1, z2, and z3. So right now explaining the associativity of complex number in algebraic operation of addition. So z1 plus z2 plus z3 is always equal to z1 plus z2 plus z3. This kind of property is known as associative property. This is also applicable for other operations like multiplication. So there is associative property, commutative property, also closure property. And always for a complex number, there exists an inverse as well as an identity complex numbers. If we take numbers, we know that there is always additive or inverse, or multiplicative inverse, additive identity, multiplicative identity, like that. In the case of complex number, we can also see that there exists uh, inverse as well as identity elements in algebraic operations of complex number like addition, multiplication. Okay, so that's it. And also we can say that another property, distributive property. So if we are dealing with two operations simultaneously, for example, addition and multiplication. Addition and multiplication, we can explain distributive property. Distributive property. So what is that? Z1 into Z2 plus Z3. We can distribute this multiplication over addition. That is Z1, Z2 plus Z1, Z3. This property is known as distributive property. The next, we are dealing with the power of iota. So, as we discussed, what is I? What is I? I equal to root of minus 1. That is, in a complex number, z equal to a plus ib. The coefficient of imaginary part, that is I, right? Okay. Then we can elaborate with the powers of I. That is normally I raised to 0, anything raised to 0, as we all know that. What? Then I raised to 1 is I. Then I square is, we know that I equal to root of minus 1. That is, I square will be, so after square rooting, then we will get I square equal to minus 1. So it's very, very important. And I cube, how we can write it as I square into I. That means I square, we have the value minus 1 into I. That is minus I. Okay, I cube. Then I raised to 4. I raised to 4 again, we can write it as I square whole square, right? I square is minus 1, then whole square. Okay, then it is 1. Okay, so we can generalize like this. We can generalize, and we can make a formula in terms of multiple in terms of 4 multiple of 4. Okay, so we can generalize like this: any power of I beyond 4, we can write it as, from 4 we can write it as I raised to 4k and I raised to 4k plus 1, I raised to 4k plus 2, and I raised to 4k plus 3. Okay, then what is I raised to 4k? I raised to 4k. The same in this order. I raised to 4k will be I square whole square. I raised to 4k will be 1. I raised to 4k plus 1. I raised to 4k plus 1 will be I, and I raised to 4k plus 2 will be I raised to 4k plus 2 will be minus 1. Then I raised to 4k plus 3 will be minus I. So these are the result. Using this result, we can solve the highest powers of I, or we can find out the highest powers of I beyond 4. 4 or beyond 4. Okay. So for example, what is the value of I raised to 25? I raised to 25. Okay, so we can write I raised to 25 as the multiple of power of multiple of 4. Okay, that is I raised to 4 into 6 plus 1. Sorry, I didn't indicate that what is k here. K is any integer. K is any integer here. K is any integer. Okay. So here we can represent I raised to 25 as I raised to 4 into 6 plus 1 in terms of just like 4k plus 1 more, right? Just like 4k plus 1. Here we know that k equal to any integer, k equal to 6. So what is the formula? What is the answer for this? I raised to 4k plus 1 equal to I. Okay. Like this, we can find any power of I. Maybe I raised to 20, 25, I raised to 3000, whatever it may be, we can use this formula to find out the highest powers of I. Okay. So that is the concept. So please ensure that you have the idea how we are deriving the powers of I from starting I raised to 0 to I raised to 4, and then just generalizing in terms of the powers of multiples of 4. I raised to 4k, I raised to 4k plus 1, I raised to 4k plus 2, and I raised to 4k plus 3. This formula is enough. These formulas are enough for finding out the highest powers of I. Okay. So that's it from the part of power of I. Then next topic is that modulus and conjugate of a complex number. Okay. Okay. If z equal to a plus ib is a complex number, then how we can find the modulus value of this complex number? Simple. Mod z equal to took the real numbers a and b, and taking their squares and adding. So this is the formula mode value of z. So and imagine, for a complex number z equal to a plus ib, that means the mode value is mod z equal to root of a square plus b square. Fine. Then the conjugate. If z is a complex number, z equal to a plus ib, then the conjugate represent z bar equal to a minus ib. Just reverse of this symbol in the center. So if z equal to a plus ib, then its conjugate will be a minus ib. If z equal to a minus ib, its conjugate z bar will be a plus ib. That's it. Then z1 by z2 whole bar, we can split z1 bar divided by z2 bar, where z2 should not z2 not equal to 0. That is a condition. Then z1 plus z2 mod z1 plus z2, we can split and write the modulus as mod z1 plus z2 is always less than or equal to mod z1 plus mod z2. So these are the properties, and the other properties are mod z1 by z2 equal to mod z1 divided by mod z2, again mod z2 not equal to 0. Then uh, z1 plus or minus z2 whole bar equal to z1 bar plus z2 bar. Again z plus z bar equal to 2 into real z, 2 real z. Z minus z bar will be 2 imaginary z, just likewise opposite. Okay. Then mod z square mod equal to, we can write it as z bar. Okay, these are the properties of modulus and conjugate function. Okay. So these are the basic ideas which should we need to learn, which should we need to realize thoroughly, so that we can make this complex numbers topic. We can make it this topic as very interesting and easy. Okay. So the next topic is how we can express a complex number in an arrogant plane, or in a complex plane, or we can call it as sometimes Gaussian plane. So for a complex number z equal to a plus ib, or maybe a complex number, for example z equal to x plus iy. So how we are expressing this complex number in an arrogant plane? So as we can express in this plane a complex number like if z equal to 2 plus i3. So here we can express in x coordinate and y coordinate respectively. The real part can be expressed in x coordinate as x coordinate, and the imaginary imaginary part can be expressed in y coordinate. Y axis. The y axis is also called imaginary axis in the representation of complex number. So we can express it as 2, 3. 2 here, this is 2 and this is 3. This is the 2, 3 point in arrogant representation of complex numbers. That's it. Okay. Okay, then let's move to the next topic, that is polar representation. Polar representation, actually this topic is erased from your already erased from your syllabus. Anyway, in the previous exams there are some questions from polar representation and also from principal arguments. So that's why I'm explaining these points or these concepts. So what is how we can express? We already expressed the complex number in an arrogant plane. So we need to represent it in polar as polar coordinates, and we need to find the argument principal values of principal argument value of complex numbers. So we are dealing with those two topics right now. So for polar representation, we can draw this is x-axis and this is y-axis. So the coordinates right here. So I am just marking a point P of x comma y. So this is the point, starts from origin, then there will generate an angle theta. Okay, so this is x and this is y. Okay, so this is the point where p and x and y is marked in this chord plane. So that is p of xy, and this is x-axis and this is y-axis. Then this distance, or this can be represented in r. Uh, r equal to root of x square plus y square. Of course, we know that. So how we represent, what are the polar coordinates? So from this angle, from origin and anti-clockwise direction, there generate an angle, that is theta. So here the angle, the sine angle, what will be the sine angle, or maybe what is sine theta here and what is cos theta here? Okay. Of course, here sine theta, as we know that sine theta always will be, sine theta always will be y over r, and cos theta, the angle, the cosine angle of this triangle, of this right angle triangle, will be x by r. So from here we can calculate x equal to r cos theta, and from here y equal to r sine theta. Okay, for a complex number, the complex number is z equal to, we know that, x plus I y. Okay, so the tangent will be, the tangent or tan theta, tan theta will be sine theta by cosine theta, that is y by r over x by r, that means y by x, or theta equal to tan inverse of y by x. Okay, so for a complex number z equal to x plus iy, the polar representation will be z equal to, we can substitute the value of x and y over this complex number, then z equal to r, sorry, r cos theta plus I into, for y we can substitute, it's r sine theta, I r sine theta. So we can take r as common, that is r of cos theta plus I sine theta. So this is the polar representation of a complex number. Okay, so I hope that you got the point, and this is the theta or the angle generated during this process. So sine theta, cos theta, sine angle, cosine angle, all are calculated from here, and we represented the complex number in polar plane. So this is the polar plane representation of a complex number. Okay, fine. Hope you got this. And how we can find the argument, the principal arguments. Principal argument of a complex number can be represented in Rz. This is argument of a complex number, principal argument of a complex number. To find out the principal argument value, we can draw a plane like this. This is the first quadrant, and this, the second, the third, and this is the fourth, of course. So of course, again, like if you represent the a complex number in a plane, if the complex number equal to z equal to x plus iy, then we can represent like this. Then of course they're generating an angle theta in counterclockwise direction. Then what is here, we can put it as the argument as theta, just theta, and it start from the theta is originating from 0 to it will be end up to this range. For the second quadrant it will be pi. So the value of theta always in the first and second quadrant will be 0 to pi, that is 0 less than theta less than pi. So here it is theta, then of course the another angle generated here, what will be the angle? So we need to find out this portion, this angle, or maybe this argument. This is, the first argument is theta, then the total will be as we mentioned, the total angle of the argument will be pi, that is total will be pi minus theta. So in the first quadrant the principal argument will be theta, and in the second quadrant the concept is less than this part, that means pi minus theta, and in the third quadrant the opposite symbol, it is always minus theta. And in the fourth quadrant, in the third quadrant, it's in the second quadrant, it will be like there will be an angle. There will be an angle generating in a clockwise manner, like this. So we need to find the angle from here to here. So as like this, minus theta will be the argument right here. So what it is, that is minus pi. The range will be 0 to minus pi right here in the third and fourth quadrant, minus pi less than or equal to theta less than or equal to 0. So minus pi, then minus theta, that is theta minus pi. Okay, so the principal arguments are in the first quadrant, that is theta, in the second quadrant, that is pi minus theta, the third quadrant it is again the minus theta reverse, and in the fourth quadrant it will be theta minus pi. Okay, so this is the principal argument value for first, second, third and fourth quadrant. Okay, so that's it. Okay, then we are moving to the properties of argument. So we discuss how we can represent a complex number in Aragon plane, or we call it as Gaussian plane or complex plane, and we also notated it the complex number in polar form as well, or polar form. And also we find out, we already find out the principal argument. We already discussed how we can find out the principal arguments of a complex number z equal to x plus iy. Next we are moving to the properties of argument. So these are the major properties of argument. So we can, as we discussed, we can write argument as arg. So argument z1 z2 equal to argument z1 plus argument z2. This is the first property. And argument z1 divided by z2 equal to argument z1 minus argument z2. And also argument, if argument z equal to 0, that means it is not defined. These are the three properties, major three properties of argument. And we have some other theorems extensions, especially when we concentrated on JE in advanced level exams, competitive exams. There is de Moivre's theorem. That is, de Moivre's theorem is said that if n is an integer, then cos theta plus I sin theta whole raised to n will be cos n theta plus I sin n theta. And also there is Euler's form is applicable to solve some problems. E raised to I theta, Euler's theorem state that E raised to I theta equal to cos theta plus I sin theta. And triangular inequality, as we know that mod z1 minus mod z2 less than or equal to mod z1 plus z2 less than or equal to mod z1 plus mod z2. So these are the major properties and theorems that we used to solve some problems in the later part. So please note it down. So we already discussed the major topics or concepts or theoretical concepts of this complex number. So we are moving towards some PYQ session. The advanced level PYQ questions, some of them are, I will illustrate some of them right here. So the first question right here is the real part of cos A plus I sin A whole raised to 6 divided by sin B plus I cos B whole raised to 8. So we need to find out the real part. So what is the real part of this complex number? So we need to find it out. So for the same, we know that Euler's theorem. So we already discussed about the Euler's theorem, and we are using Euler's theorem right here to solve this PYQ. So Euler's theorem, as we know that e raised to I theta equal to cos theta plus I sin theta. From the top, we can see that cos A plus I sin A whole raised to 6. That is the Euler's theorem expansion. Maybe we can say it as the right side of Euler's theorem. From this, we can write it as the top portion cos A plus I sin A whole raised to 6 as e raised to I theta. E raised to I theta. E raised to I, here it is theta is A. E raised to I theta whole raised to 6 by using Euler's theorem. Okay. Then the denominator. The denominator right here it is sin B plus I cos B whole raised to 8. So we can rearrange this denominator it as sin B can be rearranged in terms of cos, and cos can be rearranged in terms of sin. Because if we arrange cos B plus I sin B whole raised to 8, that means we can use Euler's theorem. We can apply Euler's theorem again in this denominator. For that, sin B, we are converting it sin B as cos of pi by 2 minus B. As we know that cos pi by 2 minus theta is sin theta. So that's why we converted that sin B into cos of pi by 2 minus B, plus we can convert cos into sin. That is I sin of, again we know that sin pi by 2 minus theta is cos theta. So here theta is B. So pi by 2 minus B whole raised to 8, right? Then again we can apply Euler's theorem in denominator as well. Then we will get e raised to 6ia divided by e raised to, here it is theta is pi by 2 minus b. So e raised to I theta, by using Euler's theorem we know that e raised to I theta. Theta means pi by 2 minus b whole raised to 8, right? Then we can elaborate this. We can elaborate this, or e raised to 6ia. This term, the denominator can be lifted up, or maybe we can write it as e raised to minus of, here it is 8i pi by 2. 8i pi by 2 means 4. Here 8 and 2 is cancelled, then 4i pi, e raised to 4i pi minus, here it is e raised to minus b into b multiplied by 8. So e raised to, it is e raised to minus 8b, minus 8b, right? Minus 8b into I. Okay. So from here, e raised to 6ia, and also we can take the third term. Third term, it is e raised to minus and minus is plus, e raised to 8bi together, and e raised to minus 4i pi. So from here we can write e raised to I into 6a plus 8b. 6a plus 8b, and we need to find the value of e raised to minus 4i pi. Okay. To find the value of, we can use Euler's theorem again, e raised to minus 4i pi, to find the value of e raised to minus 4i pi. Okay, so what is e raised to I theta? Here it is I, here theta is minus 4 pi. So e raised to I theta means minus 4 pi. Okay, then again we can apply this theorem, that is e raised to I theta is cos theta. Cos theta means cos theta minus 4 pi plus I into sin theta. Sin theta means sin minus of 4 pi. Okay, so here it is cos n pi. We know that cos n pi is minus 1. So cos 4 pi is minus 1. Here it is also there is a minus, that is minus minus 1 plus I into sin of minus 4 pi. Sin n pi is 0. So that is plus 1 plus 0 equal to 1. So in this expansion, we got that the value of e raised to minus 4 I pi is 1. So we can substitute this value. So the final answer will be e raised to minus I into, sorry. So the final answer will be e raised to I into 6a plus 8b. Right. Okay. So from here we can apply Euler's theorem again to find the real value of the given question. So by again using Euler's theorem, the given question, we simplified the given question cos a plus I sin a whole raised to 6 divided by sin b plus I cos b whole raised to 8 as e raised to I 6a plus 8b. Then again we can apply Euler's theorem. It is of the form e raised to I theta, that is e raised to I theta is cos theta plus I sin theta. That is by applying Euler's theorem again we get cos theta. Cos theta, theta means 6a plus 8b plus I into sin theta. Sin theta means 6a plus 8b. Okay. So the question is, here it is, what is the real part? So the real part is this one. So the final answer, therefore the final answer of this question, the real part is cos 6a plus 8b. This is the final answer. Okay. Yes. The next question from the PYQ is the product of omega 1 equal to 8 plus I sin theta plus 7 plus 4I cos theta and omega 2 1 plus 8I sin theta plus 4 plus 7I cos theta be alpha plus I beta. I equal to, always we know, root of minus 1. P and Q be the maximum and minimum values of alpha plus beta. Then what is P plus Q? This is the question. So we know that given omega 1 and omega 2 right here. So omega 1, we can expand omega 1 from the question, that is 8 into sin theta, that is 8 sin theta plus I sin theta plus 7 cos theta plus 4I cos theta, or we can write it as omega 1 equal to real part together, I part together, or imaginary iota part together, then 8 sin theta plus 7 cos theta plus we can put deliver I outside, then I of sin theta plus 4 cos theta. This is omega 1 right now, and same likewise we can find omega 2 as well. That is omega 2, we can rearrange omega 2 as 1 plus 8 sin 8I into sin theta, that is sin theta plus 8I sin theta plus 4 cos theta from here plus 7I cos theta. So we can rearrange again omega 2 as sin theta plus 4 cos theta together, sin theta plus 4 cos theta plus we can commonly take out I into 8 sin theta plus 7 cos theta. Okay, so this is the new omega 1 and new omega 2, expanded omega 1 and omega 2. We know that from the question, we know that if we multiply omega 1 and omega 2, we will get a new complex number, that is alpha plus I beta. So omega 1 multiplied by omega 2 equal to alpha plus I beta. So we are moving to we are going to multiply two complex number. For multiplication, we know that z1 z2 equal to AD minus BD plus I into AD plus BC. This is the formula for complex number multiplication. We already discussed about that. So right here, this if we substitute for this term, if we put A, and for this term if we put B, then automatically we can put it as, here it is C and this is D. That is, by using that formula, AD, omega 1 into omega 2, that means AD, A into D. AD, that is 8 sine theta plus 7 cos theta into multiplied by sine theta plus 4 cos theta. For convenience, we can find out AD minus BD first, the real part first. So we already multiplied AD minus, what is BD? B means this term, that is sine theta plus 4 cos theta multiplied by D. D is this term, 8 sine theta plus 7 cos theta. This is AD minus BD, the real part, that is alpha. So first of all, we need to find alpha right here, and then we will find beta in another portion. So we can expand. So right here, we can say that 8 sine theta plus 7 cos theta. 8 sine theta plus 7 cos theta, right here also. Sine theta plus 4 cos theta, here also sine theta plus 4 cos theta. That is the same, both the terms are equal. So if we deduct from one from another, it will be automatically 0. So we can find, we got the value of alpha equal to 0. The real part is 0. Then we need to find the value of beta, the imaginary part value. Okay. To find the imaginary part value, we know that from the complex number multiplication, we know that Z1 Z2 equal to AD minus BD. So we already solved this and we got the value of alpha, that is 0, and the second part is I into AD plus BC. Okay. So for that AD plus BC. So what is A? A is right here, 8 sine theta plus 7 cos theta AD. What is D? D is 8 sine theta plus 7 cos theta AD plus BC. BC, what is BC? Sine theta plus 4 cos theta into multiplied by C. C, what is C? C is sine theta plus 4 cos theta. We can see that the two terms, 8 sine theta plus 7 cos theta, 8 sine theta plus 7 cos theta. Again, here it is sine theta plus 4 cos theta, sine theta plus 4 cos theta. That means 8 sine theta plus 7 cos theta whole square plus sine theta plus 4 cos theta whole square. Then we need to expand these two terms. We will get A plus B whole square, that is first term 64 sine square theta plus 2AB, 2 into A into B, 8 into 7, that is 56 sine theta cos theta, sine theta cos theta plus 49 cos square theta, 49 cos square theta plus the next term is again sine square theta plus 2 into AB, 2 into 4 sine theta cos theta. 4 sine theta cos theta plus 16 cos square theta, right? So we can add 64 sine square theta plus sine square theta, that is 65 sine square theta, 49 cos square theta plus 16 cos square theta, that is again 65 cos square theta plus this term 2 sine theta cos theta. 2 sine theta cos theta, what is the expansion of sine 2 theta. So this term can be written as sine 2 theta. So 56 into sine 2 theta right here. Also 2 sine theta cos theta here also we can write it as sine 2 theta. So that is 4 into sine 2 theta. So that means 65, we can take 65 in common, that is sine square theta plus cos square theta plus 56 sine 2 theta plus 4 sine 2 theta, 60 sine 2 theta. That is sine square theta plus cos square theta, we know that it is 1, then 1 into 65 it is 65 plus 60 sine 2 theta. Okay, so our complex number z equal to alpha plus I beta. Here alpha is 0, beta is 65 plus 60 sine 2 theta. Okay, then in the question given that P is the maximum value and Q is the minimum value. So here it is, what will be the maximum value from this? So here P is the maximum value. Maximum value means 65 plus 60 into sine 2 theta. So for maximum, this term sine 2 theta, the value of sine 2 theta should want to be 1. So if sine 2 theta is 1, that is P will be 65 plus 60 into 1, that is 125. So the maximum value right here P is 125, and that is alpha plus beta maximum. Alpha plus beta maximum value is P is 125. Then we need to find the minimum value. That means alpha minus beta, or the minimum value. The minimum value will be, that is we denoted it as Q. So what is how we can find out Q? Q is 65 minus 60 into sine 2 theta, that is 60 into 1, that is 5. So here it is, the minimum value is Q, O is 5. Then the total alpha plus beta equal to, or P plus Q, the value of minimum and maximum is 125 plus 5, it will be 130. Okay, for the next question, this is the next question, PYQ question. The real part of a complex number z minus 2i plus divided by z plus 2i is 0. Then the maximum value of mod z minus 6 plus 8i is. So this is a question. So we need to find out the maximum value of that modulus. So let z equal to x plus iy, and the real part of the complex number is given. So we can put it as n equal to z minus 2i divided by z plus 2i. Okay, so we can substitute the value of z here in n, then we will get n equal to x plus iy minus 2i divided by x plus iy plus 2i. We can rewrite it as x plus I into y minus 2. Okay, we can take the common factor I and we can write it as y minus 2. Then x plus I into y plus 2. Okay, so we can write n equal to x plus I into y minus 2 divided by x plus I into y plus 2. Okay, then we can standardize. For standardizing this, we can multiply the conjugate, the conjugate of the denominator in both in numerator and denominator. So what is the conjugate? What is the conjugate of the denominator? The conjugate is simple, multiplying denominator in and also in numerator. Okay, so the conjugate x plus this will be x minus into I y plus 2. Okay, also x minus I into y plus 2. Then elaborating this, we will get x into x, then x square, then this first term into first term, then imaginary terms into imaginary terms, I into I square. I square is always minus 1. Minus 1 into minus, that is plus. The symbol will be plus. Then y minus 2 into y plus 2 divided by, again in denominator, x square I into I square is always minus 1, minus minus, then again it is plus. Y minus y plus 2 into y plus 2, that is y plus 2 whole square. Okay, so in question we can see that this part is 0, given that the real part of this complex number z minus 2i divided by z plus 2i is 0. That means this part is equal to 0. From this we will get x square plus y minus 2 into y plus 2, a minus b into a plus b, that is a square minus b square, that is y square minus 2 square, that is 4, equal to 0. Then from here we will get x square plus y square equal to 4, that is mod z equal to 2. The value of mod z equal to 2. Then we are moving to the next part of the question. Find the value of z. Mod z minus 6 plus 8i. So we can use triangle inequality right here. We know that the triangle inequality, mod of mod z1 minus mod z2 less than or equal to mod z1 plus mod z2 less than or equal to mod z1 plus mod z2. We can use this part. Then we can split the modulus into, this is less than or equal to mod z plus mod minus, we can take this minus inside, 6 minus 8i. Okay, so we got the value of mod z. We got the value of mod z is equal to 2. We can put it as here, it is 2. And what is the modulus value of minus 6 minus 8i? That is how we can find the modulus value of a complex number. If z is a complex number, then the mod x plus iy, then the modulus value mod z equal to root of x square plus y square. Same here, root of minus 6 square plus minus 8 square. that is less than or equal to 2 plus or minus, this will be 36 plus 64, that is 100. Root 100 means it is 10. So we can write it as mod z minus 6 plus 8i is less than or equal to 12. So the maximum value of z minus mod z minus 6 plus 8i is 12. So that's the question. So I hope you understand. Okay, so that's it from the class. So we are concluding. So if you are concentrated well, then of course the things will be not so much complex. It will be so much easy as like we discussed in the class. Complex numbers, the kingdom of complex numbers is easy to and easy to fetch, and of course we will get a better result if you work hard and if you work with passion. So wish you all the best. Thank you. Thanks a lot. Thanks for watching.